Have you ever been on one of those moving walkways at an airport? You're walking forward at your own pace, but the floor beneath you is moving too. If you walk faster, you move quickly. If you stop, you still glide forward. And if you slow down or hesitate, it might feel like you're not going anywhere, even though the walkway is still carrying you ahead. That's a lot how we experience climate change. We noticed a cold winter, or a year that doesn't break a record, and it can feel like warming has slowed or stopped. What we're seeing are short-term ups and downs, the natural variability that's layered on top of a long-term trend that is continuing in one direction. The system hasn't stopped, it's just not moving in a straight line. Today we're going to talk about the temperature illusion, why record-breaking years tend to come in clusters, why cleaning up pollution can briefly reveal more warming, and why a so-called pause in warming is usually a misunderstanding of how the climate system works. Welcome back to the podcast. I'm Dr. Mack, and this is the Climate Translation. Tell me if this sounds familiar. You're sitting around a dinner table. Maybe it's the holidays. Maybe you're in the middle of a blizzard, and the topic of climate change comes up. Someone says something like, "Okay, but if the planet is warming, why is it so cold this winter?" I hear this all the time, and the question at first may sound reasonable, and it's based on what we experience. You step outside, it's freezing, maybe even record cold in your area, and it doesn't match the idea of a warming world. But then, fast forward a few months. It's now July. You have an outdoor barbecue. The air feels humid and heavy. It's the middle of a heat wave that is breaking records all over your area. Now the same people might be saying, "Why is it so hot this year? This is miserable." You have two completely different experiences based on two opposing seasonal variations. But the root of the issue is a misunderstanding of a key concept we use all the time in climate science, but often it's not explained well. It's the difference between weather and climate. Weather is what you feel when you walk outside. It's today. It's this week. It's that cold snap, a thunderstorm, that heat wave. Weather is a short-term situation. It's local. It can swing wildly from one day to the next, or one season to the next. Climate is something different. Climate is the long-term pattern. It's the average of all those ups and downs over time, and it is typically measured over decades, not days. Here's a simple way I explain this to students in my Introduction to Meteorology classes. If the weather is your mood, the climate is your personality. Your mood can change quickly. You can have a bad day. You can have a great day. Maybe something in between. But your personality, your long-term overall pattern, it doesn't change overnight. And the same is true for the climate system. In a warming climate, we are still going to have cold days. We will still have snowstorms. We still have colder years. None of that is going to disappear. What's changing is the baseline those events are happening on. Think back to that airport walkway that I discussed in the opening. The short-term ups and downs, the colder or warmer winter, or the milder or more extreme summer, those are your footsteps. Just like you can sometimes move faster and sometimes slower, the climate can sometimes be cooler or warmer than usual. But the walkway underneath, that's the long-term warming trend. It's still moving. And in the case of the climate of our planet, it's moving in an upward trajectory. Averages and trends are harder to visualize and understand. We as humans have short-term memories. The here and now is often more important and impactful to us. People expect climate change to look like a smooth, steady increase, like a line on a graph that just goes up a little bit every single year. But that's not how our Earth behaves. The climate system is influenced by many moving parts, many of which we've discussed in this podcast in the past. Ocean cycles like El Niño, La Niña, volcanic eruptions, changes in air pollution, the natural variability in the atmosphere. All of these can push temperatures up and down in the short term. So when you zoom in and look at a single year, or even a handful of years, it can look messy. It can look flat, it can look like it's going in the wrong direction, but when you zoom out and plot things over decades, the picture becomes more clear. Over the last century, the global average temperature has increased by a bit over a degree Celsius, or 2 degrees Fahrenheit. But that increase hasn't been a straight line. If you've seen these charts online or in the news, they look more like a wobbling staircase. Another way to think of it is this. Imagine you're on a busy interstate in a large metropolitan city. There are drivers all around you. Some of the drivers are driving fast. Some are driving slow. Some are influenced by the car they're driving, the age they are, the grade of the road, even the driver in front or behind them. Perhaps, at times, you're stuck behind someone who's moving slower, so you weave your way to where someone's moving faster. It's hard for you to get a handle on how long it will take you to get to your destination, or what the overall traffic pattern is like. However, if you were to get into a drone and zoom up above the roadway, you might notice that the overall trend is the speed is increasing over time when taken as an average. There are a lot of variables in the atmosphere that lead to our short-term weather, but when taken together, we can get an overall pattern of the trend lines in the average. What makes things more complicated is that the extreme years, the cold winters or the hot summers, don't show up randomly like they used to in the past. We're starting to see them occur in groups, and that pattern, those clusters, is one of the clearest signals that the underlying system is changing. The past decade or so has given a lot of climate scientists cause for concern. I mentioned that the overall trend line is upward, but the extreme years, the years where we seem to be breaking records across the globe, they're happening more frequently. You'll hear something like, this was the hottest year on record, and then the next year, it's broken again, and then again. It can start to feel like instead of records being broken, they're constantly being surpassed and replaced. So what's going on? Why do hot years cluster together instead of being spread out? When we look back at the historical climate record from the past million years or so, we can see a mix of cooler years, average years, and warmer years. Sometimes the trend line went up, sometimes it went down, but on average things were relatively stable. However, recently, because of human influence, primarily the production of carbon dioxide from industrialization, the baseline average has shifted. The mean has been altered. Think of a pair of dice. In the past, the climate system was like rolling a fairly balanced set. At any given roll, you have an equal chance of getting a cool year, an average year, or a warm year. But now let's say someone slowly added weight to the dice, specifically towards the higher numbers. You can still roll a low number. That hasn't disappeared, but the odds have shifted. Now high numbers come up more often, and sometimes they come up several times in a row. In the historical climate record, we've seen this due to natural variability. Perhaps a volcano explosion led to cooling globally. We've seen ice ages. But now we're seeing anthropogenic warming due to human influence that's raising the baseline temperature of the planet. Because of greenhouse gases, carbon dioxide, methane, and others, we're trapping more heat in the system. That in turn raises the floor that all weather sits on. So today, even a cool year by modern standards is often warmer than what used to be considered average just a few decades ago. That's the first piece of the cluster effect, but there's more going on. The second piece has to do where more heat is stored. I've mentioned before that over 90% of the excess heat in global warming doesn't stay in the air, it goes into the oceans. And the oceans don't release that heat all at once. They store it, and then they release it gradually over time. That means once the system warms up, it tends to stay warm. You don't just get one hot year, you get several, because the ocean is feeding that heat back into the atmosphere year after year. Now there's a third piece that can shape how these clusters feel at a regional level. Some research suggests that as the Arctic warms faster than the rest of the planet, it can affect the jet stream, the fast-moving river of air that steers weather systems. When the temperature difference between the Arctic and the equator weakens, the jet stream can become more wavy and slower moving. Weather can get stuck in those processes. Heat can sit over regions for longer periods, or cold air can linger in one place longer than usual. It's an active area of research, and scientists are still working to understand exactly what the connection is. But what we're confident about is this: there is a rising baseline, and that's a foundation of everything else. In my earlier episode, The Invisible Mirrors, we talked about aerosols, which are tiny particles in the air produced by things like burning coal, diesel engines, and wildfires. Some of these particulates act like mirrors. They can reflect a portion of the sunlight back into space before it reaches the surface. And when that happens, the planet can cool slightly, especially in certain regions. But it's not enough to stop the average global warming across the planet, but it's enough to mask it. You can think of it like a thin veil over the system. The heat from the greenhouse gases is still building underneath, but not all of it is showing up at the surface right away. For much of the 20th century, especially in heavily industrialized regions, the effect was significant. Air pollution was high, aerosols were abundant, and in some places they were reflecting enough sunlight to offset some warming caused by greenhouse gases. But particulates like these don't stay in the atmosphere very long. They fall out in weeks to months, which means they only stick around if we keep emitting them. And over the past decade, we've started cleaning the air. Regulations in the United States, Europe, and parts of Asia have reduced sulfur pollution and other aerosol-producing emissions. From a public health standpoint, it's a huge success story. Cleaner air has saved millions of lives. But from a climate perspective, it comes with an interesting side effect. As we remove those reflective particles, we remove the mask. And when that happens, more of the underlying warming that was already there becomes visible. This helps explain something that can otherwise feel confusing: why warming doesn't always appear gradual, why certain decades seem to heat up faster than others, and why, in combination with that cluster effect we just talked about, record-breaking years can seem to arrive all at once. Without the noise, without that veil, you can see the climate trends more clearly. And this is one of the reasons climate scientists can feel counterintuitive to some. Sometimes progress in one area, like cleaning air, can temporarily make the problem look worse. But the reality is, it's not making it worse, it's removing the filter. And once that filter's gone, the underlying trend is becoming harder to ignore. The climate of the Earth is complex. It's not as simple as looking at a graph or a chart to determine what's going to happen next. When we have regional variations or a mild year or season, it can be confusing. I think this is one of the reasons we hear things like, "Did global warming stop for a while?" or "I read temperatures haven't increased the last few years." This idea of a pause in warming has shown up periodically. And like a lot of misconceptions, it comes from looking at the right data, but asking the wrong question. Climate change doesn't disappear just because one year is less extreme than the other before it. We have baked in a trajectory based on our rapid production of greenhouse gases over the past few centuries. When you see news stories or hear people talk about a pause in warming or a change in the weather, they're focusing on a very short slice of time, months or even years, and expecting it to behave like a long-term trend. But as we've stated, the climate system doesn't work that way. Year-to-year temperatures are influenced by natural variability, things like El Niño and La Niña and those volcanic eruptions, even ocean cycles. Those factors temporarily can push temperatures up or down. If you start picking a point that happens to be a warm year, maybe like a strong El Niño year, and then compare it to years that follow, the trend can look flat or even reduced. But that doesn't mean global warming has stopped or reversed. It's the system fluctuating on top of a rising baseline. This is something we can clearly see in long-term data. If you look at global temperatures over decades and centuries, the upward trend is unmistakable. But if you zoom in too closely, just a few years at a time, you can find short periods that look like pauses. I guess when it comes down to it, it's a matter of scale. It's kind of like looking at the stock market. On any given day, prices can go up or down. Over a week, you might see a dip, but that doesn't tell you the long-term direction of the market. To understand that, you have to step back and look at the bigger picture. The same is true of climate. Short-term variability is not canceling out long-term trends. And in fact, when scientists study these so-called pause periods, they find the energy in the system never stopped increasing. The oceans continued to absorb heat. The planet continued to gain energy overall. It just wasn't all showing up in the surface air temperatures in a short time. So the idea of a pause or a reduction in warming isn't really about the climate stopping or reversing direction. It's about where we're looking and how much time we're looking at. When we focus on narrow windows, it can be easy to miss the larger pattern. By zooming out, the signal becomes clear. That moving walkway is still moving forward. The Earth's baseline is still rising. Average temperatures are still increasing. And short-term slowdowns are just part of how a complex system behaves. The changes in our planet's climate aren't going to show up like a straight line on a graph. There are going to be times when we have lower, average, or warmer years. But what's more important is the average, that trend line. That is the difference between weather and climate. Cold winters don't disprove warming. Hot summers don't define it. And a few quiet years don't mean it stopped. What matters is the overall direction of the system over time. When we step back far enough and truly look at what the data is telling us, the direction is clear. The baseline is rising. Our odds are shifting. And the patterns we're seeing are exactly what we expect from a global system that's warming. It's time to move past the rhetoric and the confusion and see the climate system for what it truly is. Very complex, but reacting to human inputs. And we can expect those reactions to become more evident as time passes. I'm Dr. Mack, and this has been The Climate Translation. If you have a question about the climate you've been too afraid to ask, or if you have a differing opinion, I want to hear from you. I can use your viewpoints in future episodes. You can reach me at theclimatetranslation@gmail.com. I'll see you next time.